If you're watching this, you probably know what a Raspberry Pi is. If you don't, it's basically a small credit card sized computer that costs $35. The CPU doesn't produce very much heat. In fact, you can run it without any cooling at all. A small heatsink and fan will easily keep it cool enough even under full load for extended periods. What that means is that what I have done is totally and completely unnecessary. Overkill in the extreme. You see, I didn't just water cool it, I made a chiller too. I decided to 3D print as many of the water cooling parts as possible. I started off by designing the CPU cooling block. A standard 14mm Raspberry Pi heatsink slots into the bottom. To mount the cooling block, I remixed this case from Thingiverse. The top of the case holds the cooling block firmly against the CPU. The chiller is made from a Peltier and 4 more 14mm heatsinks. More on how this works in a second. I printed the parts on my Ender 3 in Ziltech PLA at 0.1mm layer height with reduced speed and 100% infill. I also raised the temp slightly to help seal any gaps. I was concerned that the 3D printed parts would leak, but aside from a small easily sealed leak in the chiller box, they held water perfectly. Back to the chiller. I'm using a Peltier module, technically a thermoelectric cooler TEC or TEC that uses the Peltier effect. It seems Peltier and TEC are often used interchangeably when referring to these modules. I'll be calling it a TEC, both because that's more accurate and easier to pronounce. So, what is it and how does it work? According to Wikipedia, when a DC electric current flows through the device, it brings heat from one side to the other, so that one side gets cooler while the other gets hotter. Put simply, it moves heat. So here's the plan. The water is chilled by circulating past the cold side of the TEC. The TEC will transfer heat to the hot side, and a separate cooling loop will dissipate heat from the hot side into the air via a radiator. Both sides will need their own reservoir and pump. There's one big problem with water-chilled cooling loops: condensation. If the temperature of the cold side falls below the dew point, condensation will start to form and drip into the electronics. To solve this problem, I'm going to make a control system for the TEC, basically a fancy thermostat. An Arduino will use a temperature and humidity sensor to calculate the dew point. Another temperature sensor will be used to measure the water temperature. When the temperature of the water gets too close to the dew point, the relay will turn the TEC off. I added a small OLED display to show the ambient temperature, water temperature, and target temperature. I threw together a rough plan of what I wanted it to look like in SketchUp, then got a little carried away with Blender and made this. Let's get to the build. Now that it's up and running, it's time to do some overclocking and get some temperatures. To access the Raspberry Pi, all I have to do is log in from VNC on my desktop. After a couple hours of messing around with overclocking, I was only able to get it stable at 1.55 GHz, a 150 MHz overclock. From what I've read, other factors besides temperature limit the overclocking potential of ARM chips, and that's why I'm not able to overclock this to say 3 GHz just because it has awesome cooling. With no cooler, it idled at roughly 37 degrees, and under load, it quickly shot to 70 and began throttling. At stock clock speed with the chiller, it idled at 12 to 14 degrees. After 15 minutes under full load, it reached 17.6 degrees. While overclocked to 1.55 GHz, it idled approximately 1 degree warmer and reached a temperature of 18.2 degrees after 15 minutes under load. This project only cost me a total of about $18.93. However, I already had most of the parts, and those that I didn't have I was able to find for free or cheap. For example, the LED strips are backlights salvaged from a dead TV, the pump on the cold side came from an old fountain, and I pulled the power supply out of an old PC. If you were to build this from scratch, it would cost you about $120. That's assuming you can get the power supply and fan for free. Computer shops are often happy to give you an old low-capacity power supply for free. I was able to get the AIO that's cooling the hot side for about $7.50 on eBay. If you aren't able to find a deal like that, it could easily cost you another $40, bringing the total to around $160.